Okay, YouTube, this is my first video on nonlinear inequalities in which we're explicitly going to be graphing quadratic inequalities in two variables. And basically what I'm going to do is I'm going to walk us through the steps on how we complete this process here. But basically what we're going to be doing is still graphing quadratic things but shading on one side or the other of this, and we'll talk about why. So to graph a quadratic inequality in one of the forms above, it says follow these steps. And of course in one of the forms above, what I'm going to tell you is that we're going to have something that maybe looks like this right here. Now what I got to tell you is I didn't list the quote-unquote forms above, but this is a quadratic inequality that has two variables, and you'll notice that the only difference between a quadratic equation and a quadratic inequality is that we either have a greater than or equal to, less than or equal to, greater than or less than relationship between our y side and our x side here. So essentially, when we graph these, step number one is always going to be to graph the parabola with the equation y equals ax squared plus bx plus c. And then I note here, or it is noted here, make the parabola dashed for inequalities containing a less than or greater than, and solid for inequalities containing a less than or equal to or greater than or equal to. So let's go ahead and take a look at this first example here, and we'll just talk about this first step. Essentially, when we want to graph this here that says y is less than this quadratic thing in standard form on the right side, the first step we're always going to do is we're going to go graph this as if there were an equal sign there to begin with. Okay. So now, knowing that this is in standard form and I want to graph this, the very first things we're going to find are the axis of symmetry and then the vertex values here, and then we're going to go and use our a value to sketch the rest of this. So as far as the axis of symmetry is concerned, remember that when this is in standard form, it's always x equals negative b over 2a. So in our particular instance here, we have a b value of negative 4, so we get negative 4, negative 4, and this would be over 2 times a, where our a value is negative 1. And so in this case, we get positive 4 over a negative 2, which gives us a negative 2. So now knowing where this axis of symmetry is, I'm going to go ahead and put this on our graph here. We're going to say at negative 2, we have this axis that runs through the middle of our parabola here. We say x equals negative 2 is its equation. And also knowing that negative 2 is the x value of the axis of symmetry is also the x value of our vertex value. So we'd say negative 2 and f of negative 2, we certainly need to go find what f of negative 2 is, or what our y value is when x is equal to negative 2. So to do this, we're just going to plug negative 2 into our original function, which gives us negative blank squared minus 4 times that same input minus 3. And we'll just go ahead and put in our negative 2 here, and we'll evaluate this for the y value. So kind of building upward here. I'll try to quarantine this here. We would say negative positive 4, so we get a negative positive 4 when we square this. A negative 4 times a negative 2 is a positive 8, and then minus 3. So this negative 4 and the positive 8 give us a positive 4 minus 3 here, and we get 1. So our vertex value must be at the point negative 2, 1, positive 1. And so now that we have the vertex value, we'll go put this on the graph. We say negative 2, comma 1. So this point is on here. So now going back up to step 1, here I'm about to graph this. What I want to point out is this. It says make a dashed parabola for inequalities that have a less than or greater than, which we do in this case have just a less than, but a solid for inequalities with a less than or equal to or greater than or equal to. Using the fact that our a value is a negative 1, I know that as we go to the right one, we're going to go down 1. And I also know that this point would be on the graph here, but basically what we're intending to say here is that we should make a parabola that is dashed like this. And because, here's the deal. When we are looking at an equation, say this equation right here, and you graph this parabola, the sheer fact is if you are a point on this parabola right here, like negative 2, 1 is a point on this parabola, if we were to go plug in 1 for our y value and plug in negative 2 for the x value here, everywhere you see an x, you would get a true statement. That is to say that all the points on this parabola, when you plug them back in, make this statement true. In this particular case, since we're looking at quadratic inequalities, basically what we're saying is only those things that are less than this expression here, only the y values less than all of this right here, make it true. So because it's not less than or equal to, we wouldn't include any of the points that are actually on the parabola, because if we were to plug that back in, I mean, we would almost get a true statement. We would get something like negative 2 is less than negative 2. So if we had had an or equals to here, it would be true. But since it's not an or equals to, what we're going to do is we're going to put a dashed parabola to kind of indicate that nothing on the actual curve satisfies this. So step number one, basically go graph the parabola. We'll use a dash it if we have a less than or greater than, and a solid if we have or equals to in there. So step two says, let's test a point xy either inside the parabola or outside the parabola to determine whether the solution is an inequality. So this suggests that we should always test a point inside the parabola to determine whether the point is a solution of the inequality. What I'm going to suggest is we're going to test a point either inside or outside that is not on the parabola. So I notice here that 0, 0, and I'm going to use 0, 0 because it's a convenient point. What we're going to do is we're going to plug this in and we're going to say, is it a solution of this original inequality? So looking at the inequality, we have y is 0 is less than negative 0 squared minus 4 times 0 minus 3. And what we end up with is this statement. We get 0 is less than, and these cancel out here, negative 3. So the question is really, is 0 less than negative 3? And because I know 0 is to the right of negative 3 on the number line, this is actually a false statement. So what this means for us is that this point 0, 0 does not satisfy the initial inequality. But what I'm going to tell you is all of the points either on the inside of the parabola or the outside must be solutions or not solutions. So the moment that I know that 0, 0 is not a solution, this doesn't work, then I know that all points on the outside of the parabola also do not work. So since we shade points that are solutions on a graph, what we're going to do is we're going to shade the inside of this parabola right here. And what we're really doing here is we're saying if you were to pick any point in this shaded region and plug it back into the original inequality, you would get a true statement. So that's why we're shading them, is because these are the things that make our inequality true. So what I'd like to do is graph this next one here. We're going to go a little bit more quickly on this one. We say y is less than or equal to x squared minus 2x plus 1. And so in this case, we would say what we're going to do first is we're going to go graph the equation y equals x squared minus 2x plus 1. So again, the axis of symmetry, we're going to need to find this first. We have negative b over 2a, so negative b, which is negative negative 2, all over 2 times a here, where our a value is 1. So we would get this. We would get a positive 2 over a positive 2, which is 1. So we know that at x equals 1, we have our axis of symmetry here, and we should label this x equals 1. So now the next step is going to be to find the vertex value here. So we'll plug in 1 for our x value. We need to go find f of 1 for the y value. So now plugging in f of 1 here, it seems that we would get f of 1 equals 1 squared minus 2 times 1 plus 1, which comes out to be this. We would say 1 squared is 1 minus 2 plus 1, which is negative 1 plus 1, which we get 0. So this means that our vertex value here is really at the point 1 comma 0. So our vertex is actually a 0 of this function here. And we'd say using the a value of 1, I know that as I go to the right one, I would only go up 1. And because of symmetry, this must be on our graph. So to finish sketching this, the first thing we're going to do is ascertain whether or not we should use a solid or a dashed line. And because this is a less than or equal to, we actually do want to include all the points on the outside of this parabola here. So let me try this again. That's better. And we'll use a solid path on our parabola there. So now what we're going to do is we're going to choose a point to plug into the initial inequality and test. And what we're really testing is, does that point make it true or not? So I notice that 0, 0 is not actually on the curve. I want to know whether 0, 0 when I plug it in makes this true or not. So we'll plug in 0 for our y is less than or equal to 0 squared minus 2 times 0 plus 1. And so in this case we get 0 is less than or equal to, and these cancel out again, 1. So since 0 is indeed less than or equal to 1, what we notice is that 0, 0 is a point that satisfied this initial inequality. And because it's true, we should shade it. But what I want to point out is, if it's true, then all of the points on the outside of this parabola must also be true. So what we would do is we would shade all of the points on the outside of the parabola, saying that they must satisfy the original inequality and that none of the points on the inside of the inequality must be satisfied with this. But that is how you graph a quadratic inequality. You essentially graph your parabola, taking note of solid or dash it, and then you test the point and shade toward the side of the parabola that contains all the points and make it true. Cheers.